Very happy to be here and excited to be in this session and to be presenting in this very beautiful venue. My name is Navdeep Sahni. I'm from Stanford University. And this is joint work with Yixin, Tang, and Nicole.lin at DoorDash. So who's this paper for? What is this paper about? If you've ever done an A/B test, if you use experimentation for evaluation of policies or for testing innovation, and if you've experienced delays or even stoppage of work because of the A/B test being a bottleneck, this paper is for you. Basically, we are trying to understand how we can speed up A/B testing and therefore innovation. Okay. Let's jump right into a problem, and then later on we can zoom out from here. So let's think about the problem that a marketing manager at DoorDash faces. Okay, so DoorDash is the largest delivery platform in the US. It's a publicly traded company. It's known that they have a very big marketing budget, upwards of $1 billion. For the promotion team, the budget is also pretty large. It's of the order of a big chunk of the whole slice. Now the goal of the marketing manager is to optimize the promotions that they send. And optimization is not just about the message that they put in the promotion, but the degree of intensity of the discount, when should the discount be given, at what frequency it should be given. So it's a very complicated policy that they have to make. And the goal is how to come up with the best promotion policy. Okay? That is the goal. The question is, how can we answer this question? How can we identify which is the best promotion policy? Now, the statistics literature, the business statistics literature provides a very powerful tool to understand causality, and which would be like, should I go with policy 1 or policy 2? And that is A/B testing. So it can be A/B or A/B/C/D. It can be scaled at many different levels. Could A/B testing be the answer to this question? Can we apply that methodology? The appealing thing about A/B testing is that it is very, very clean. It's causal. It measures the effect of actually implementing the policy that is under question. So that is very appealing about it. However, there are many challenges that are practical in implementation of A/B testing, which are prevalent everywhere, but not talked about as explicitly, even in academia or in practice as much as I've seen. The first challenge is that A/B testing, for all its power, requires implementing of all the policies that you actually want to test. So if you want to test a policy, you implement it and run it against the other one. There are certain policies which are going to be easy to implement, like the color of a button on a web page. That's very easy to change. However, for bigger decisions like this one, this is a digital business. DoorDash is a totally digital business. Promotions is one of the components. Setting up a policy takes a lot of actions that have to be done at the same time. So in this case, you got to come up with randomization. So every user has to be randomized into one of the different bins. Then that randomization has to be mapped to a promo code. You need to make sure that the promo code is given to the customer across the different channels. You need to make sure that it expires at the right time, and this is going to be different for different groups. Then you need to make sure that the back end, the service team knows about it, so that if the customer calls the service team later on, they are aware of it. So it's just a very, very complicated problem, the implementation of these policies. And we measured this in our context. To implement one policy, it takes one person, one operator week. If you want to do a 24 policy test, it's going to take either 6 operators for a month or one operator for a long time. So it's a very, very involved process. At the same time, because this involves a lot of coordination across teams, there are a lot of errors that happen. Here is an example from the public domain. So Upworthy is a company that did a lot of experiments and made the data available to researchers. Very recently, so there have been papers that have been published with it. And recently, so a couple of months ago, we found that a lot of the experiments that were done by Upworthy were not balanced. So they were not correctly done. And 22% of them had errors. So if the implementation of an A/B test has an error, the outcome is going to be erratic as well, because that will make us make wrong decisions. In my own example, I've been working with companies in the past also. About 30% of the experiments that I get from companies, there is one error or the other. So this is also a major challenge that we need to keep in mind if we are thinking of using A/B testing. Okay, so that is one, but that is not enough. In large companies, the effect sizes that we are going after, so a 1% increase in the revenue can be huge. And we want to test, we want our A/B test to be able to give us, to identify these small effects. But to identify these small effects, we need very, very large data, and that delays A/B tests even more. So that is another problem. And that is not enough. Another thing we've seen is that most of the A/B tests are actually null results. So we were talking about it earlier. From publicly known data, Optimizely is one company that provides A/B testing infrastructure. They report that only 12% of A/B tests are actually successful. Okay? So if there are 100 A/B tests running, 12 of them are going to be significant, 88 are not going to be significant. Similar data is coming out of Microsoft, Expedia, and the success rate of A/B testing. So these are tests that are actually approved to be run. The success rate is very, very small. So what does it mean? It means that conditional on a test being successful, there is a very, very large false positive rate. It means that if there is an A/B test that actually goes through, there is a chance that 30% of the successful A/B tests are actually false positives, because 5% of overall tests are going to be significant just by chance. So this is a very, very big problem. Okay? Because of all these challenges, A/B testing does not play as big a role as we would think, because it's a very simple, very convincing way, a very clean way to judge policies. It does not play as big a role. So therefore, what ends up happening is the status quo that we saw at DoorDash and we see in other settings as well. So there is theorizing, there is brainstorming, and then there's a shortlisting of candidate policies. There's a big, big shortlisting. And that shortlist goes to the A/B test, and then they adopt the winner, and then you continue the innovation process. So that is the status quo that we are seeing. So a consequence of that is that the optimal policy might get lost. It may never get tested, especially when we know that the intuitive tests are not very significant. So the intuition is not playing that big a role. And then A/B testing becomes a bottleneck. Data-based innovation is taking a backseat in this process. Okay, so this is the problem that we are facing, and we want to solve, and we want to improve this. Okay, so what did we do at DoorDash? We use fractional factorial designs that I will explain in a bit how we actually do it. Using this in a nutshell, we have deployed this at DoorDash, and we are able to, in the example I'm going to show you right now, we are able to improve revenues by 7%. And at the scale of DoorDash, this is a very large number. Due to our methodology, the experimentation setup cost goes down by 67%. The speed of experimentation, which is the big frustration I was talking about earlier, increases by 267%. And the way experimentation is done at DoorDash is the way we are thinking about experimentation is also changing. And I'll elaborate on that in a bit. Okay. So how do we go about doing this, and how does it differ from our benchmark of a standard A/B testing? The first thing we do, inspired by the literature on conjoint analysis, we first want to factorize the policies that we are thinking about. Okay? So when we think about a policy, we don't think of it as a monolith. We think of it as a component of multiple different factors. That is the first step. In our setting, we are thinking of 4 different factors that make a promotion policy. One is promo spread. It could be upfront that you give to the customer in the beginning, or it could be spread out over time. Then the way the discount is framed, so we are not changing the intensity of the discount over here, but the way the discount is framed could be either free shipping or a similar amount in terms of percentage off, or a similar amount in terms of dollars off. So these are just different framings. It could be triggered at the weekend when the traffic is high, or it could be triggered uniformly in an ongoing manner. It could be recommending a merchant specifically, or it could be a general message. So these are 4 different factors, and we have multiple levels that we can think of those factors. Right? So this is a step that we borrow from multivariate statistics and from conjoint analysis. The next steps are going to be very different because unlike conjoint analysis, we are not doing a survey. We are not doing a within customer analysis. We are doing a cross-sectional analysis. So next, we want to get to experiment design. If we look at all possible combinations that are feasible from these, we have a lot of combinations. We could come up with 24 different policies that we can come up with from these combinations. However, if we want to estimate all these 24 combinations, we will be estimating a model like this one with a lot of parameters, and the experiment design needed to estimate all of these is going to be very complicated. So what we did in this context is we simplified our model. We said, OK, we are going to assume that the interaction between these factors is not there. It's insignificant. It's immaterial. What does it mean? It means that we are assuming that free shipping works the same way as given on a weekend versus when it's given ongoing. So that is the interaction that we are assuming away for the purpose. And that is going to give us some gains in the implementation side. So here we assumed, so this doesn't have to be, but here we assume that there is no interaction. When we do that, we are basically assuming away that all these other parameters are 0. So what that buys us, it buys us that we can now test 24 different policies at the cost of implementing only 8. So that is the 1/3 cost that we are actually paying of testing all of these 24. And not just that, when we do a power calculation based on factorial designs, which is different from what we do in typical A/B testing and described in the paper, the sample size that is needed also goes down by about 1/3. It's about a third of it. So that is going to help us increase the speed of experimentation. So these are the gains that we make from making that assumption. OK, but now that we've made that assumption, is it a good assumption? That is a question. The first point I want to make is that if this has to be a scalable framework, then we got to think about a framework that actually rigorously tests these assumptions. That's something we got to get into in a bit. The second point I want to make is that the companies are actually making this assumption implicitly, because if we are doing these tests sequentially and we are not testing all these policies simultaneously, we are actually implicitly assuming that the interactions aren't there in many cases. So what this test does is it brings this assumption out in the open and gives us a chance to actually test it. But this assumption was being made in the status quo already. OK. Now, if you want to make an evaluation framework that accommodates this fractional factorial design, we got to come up with a framework to test this assumption. So what we did to test this assumption is we launch another additional arm, which is held out from the model. So this 9th arm is not fed into a model. That is held out. And now, after the data is being gathered, we're going to compare the model's prediction for the, sorry, this is not working, but the model's prediction of the 9th arm versus the first arm. So we have 8 experimental arms which are in the model, and the 9th one is held out. So what we do is, on the left-hand side, we predict from the model what would happen in the 9th arm and look at what the model predicts would be the change from the first versus the 9th arm. And then we actually use the data to validate whether these two things are actually equal. We do that with the first experimental arm, the second, third, fourth, up to the 9th one. So now we have 8 different tests of our assumption that we made in the beginning. So we can do that, but we can do much more than that, because we can do this test not just for the overall sample, but we can do that for different profiles of customers and make sure that this assumption holds in different cuts of the sample that we have. So this way we can test the assumption. OK, so we have a framework for testing the assumption that we are making to simplify our task. How can we evaluate what are we getting out of this experiment? So for every given individual that comes with a profile is represented by X over here. All we do is we predict using our model what would be the Y variable, which in this case is the revenue minus the promotion cost. And then we assign to that individual the best out of the 24 policies. So now we are not just relying on the 8 experimental policies, but all the 24 combinations. So for every individual now, we know what is the best policy. and then we can estimate the gains from using the fractional factorial design, because for our sample, we can calculate the average gains of the winning policy minus the control policy, and that'll give us the gains from using this fractional factorial design. Okay, so jumping into the results, the first thing we did after this experiment was done is to validate, okay, did the model assumption actually hold in the data? And the assumption was no interaction. So what we have over here is a picture where on the x-axis we have the change between, so the actual change in the data between arm 1 and arm 9, arm 2 and arm 9. 9 was the held out arm. So we have 8 different data points over here. And on the y-axis, we have the predicted ones, which our model predicted without seeing the data on the 9th arm. Okay? And we see that this, when the actual difference was high, the predicted distance was equally high. When the actual difference was low, the predicted difference was also low. And we do the same thing for different y variables. We do the same thing for different cuts of the customer profile. Okay, so this, and then doing a statistical test on this, even looking at the quantitative slope of the line, we are unable to reject that the assumption is okay to make in this context. But this can be done in another context, and you can actually check whether the assumption is okay or not. Okay. Now this design doesn't just tell us the winning policy, but also tells us something more. It teaches us more than that. It tells us what actually works in this context and what doesn't. So to learn something general, what we did over here is we look at the different factors that we had in the beginning, and we are aligning them in an increasing order of how consequential those factors are. Basically, what this tells us is that the discount framing was the most consequential for DoorDash. So going from the worst to the best discount framing, we make the biggest impact. The trigger timing, whether it happens on the weekend or if it's ongoing, that is not very impactful. That factor doesn't really matter overall. The winning policy for DoorDash on average is giving a percentage off framing of the same discount, upfront promo spread rather than keeping it spread out over time, putting a generic message versus giving a specific merchant recommendation, and an ongoing rolling of this works best for them. Okay, so this is the overall. Now we got to go from here to the personalized policies that we care about. So we marry the fractional factorial design with techniques of estimating heterogeneous treatment effects. What we find is that if we do a blanket approach where we get a lot of data and we just throw a lot of interactions into the model, we don't identify anything. So the overall result is almost, so we don't see any systematic heterogeneity in the effects. However, we picked past spending, which we knew from our observational data analysis is that it is really predictive of people's behaviors. And if we segment individuals based on their pre-experimental spending, we see that that covariate has a lot of bite. So basically, we find that this interaction of our factors with the spending profile of the individual prior to the experiment is quite significant. And so some of the numbers I've shown you earlier, I just want to break them down a little more. So what we found is that the predicted profit that we get from the optimal policy is 1% higher from what we had within the implemented 8 policy. So that is the gain from doing the prediction that we did using our model. And it is 5% higher compared to the control. If we do not do the heterogeneous treatment effects, we lose out on 2% of the gains from the profit. So the last step of going towards personalized policies, using fractional factorial designs, we get 2% more in the incremental revenue. And of course, the setup cost and the speed of experimentation are both improving. Okay, so this got deployed at DoorDash. It's implemented over there. We got, we heard from the leadership at DoorDash. I just want to, we submitted the full letters with the paper, but I want to emphasize a few things that we heard. So this is from Gunn Johnson, who is the VP of product at DoorDash. He says that So this project and our fractional factorial design approach changed the way the whole organization thinks about designing experiments, and factorization is now a part of how they think about experimentation. There's a separate engineering team that is building an experimentation platform. So an experimentation platform is an internal tool that product managers and program managers see, and they input their A/B tests into that. So they are building factorial design into that experimentation platform, which urges the experimenters to think about the factors, and based on the factors, it suggests different designs, and they can choose a design based on their intuition. And this is work in progress. Okay. So zooming out from the DoorDash context, A/B testing is a very simple and very theoretically clean tool for all kinds of tests. Implementation becomes difficult for high-stake decisions, and in those decisions, this kind of a framework that was the status quo going in is quite common. What we are suggesting is a slightly different framework. What this buys us is, so instead of specifying a short list of policies, we urge experimenters, decision makers to think about what is the fundamental factors that they're actually testing. Once those factors and their levels are identified, the design implements a subset of the total combination of policies and then evaluates all of them and gives out a personalized recommendation for every experimental unit on what would be the optimal policy for that unit. And it doesn't just do that. Because the factorization job is already done, we are able to learn something more fundamental, a bit more fundamental than what we learn from A/B testing, because we just don't learn what is the best policy. We learn what factors actually worked, what levels are the best. So that intuition can feed into theorizing, and then A/B testing can actually play a better role in the whole brainstorming process, and rather than just identifying the best policy. Okay, so the paper also makes some contributions to the academic literature. So this is, to the best of our knowledge, the first actual implementation of fractional factorial designs with heterogeneous treatment effects. So the heterogeneous treatment effects using machine learning is a relatively new area in marketing, and this combines both these things, and we have a deployed proof of concept using an out-of-sample arm, which tests the assumptions made in the fractional designs. And this complements the literature which is focused on practice. The problems with the power in A/B testing are well known. It's known that it requires very, very large samples, and the success rates are very low. This literature is mostly focusing on using better and better controls to improve power. Our approach, it complements that, because we are not just improving the controls. We are saying, let's just design the experiment a little better for better learning and more efficient learning, and improve the speed. So this is different from other approaches like that we compare in the paper, like multi-arm banded, because all those other approaches require implementing of all the candidate policies, and we don't require that in this design. And this is now forthcoming at KDD. Okay, to summarize, what are the key takeaways here? So I do a lot of experimentation, and by experimentation, I mean complicated A/B tests in collaboration with companies. That is A/B testing is a very clean tool, very easy to analyze tool that we get from business statistics. When we take it to practice, we see that it becomes a bottleneck. It is challenging because of the reasons I mentioned earlier. And fractional factorial designs help us a way to improve the efficiency of learning. It puts A/B testing a little more central and not just an evaluation tool ex post that we can use. And combining this with heterogeneous treatment effects can give us much more powerful takeaways. Thank you, and happy to take questions.
Thank you so much. Now I will take some questions from the judges. Hey, hi. Hey, how you doing? First question. So you talked about the 5% increase in revenue. This seems to be assuming, given your data and assuming your model. So it's like within the model, within the data. Have you tried to do any kind of impact quantification using maybe holdout samples or holdout arms? To get a bit more kind of confidence there's no overfitting, or how do you account for uncertainty, sampling in the...
Yeah, so great question. So you're referring to the evaluation framework that we used towards the end. So in the paper, we talk about multiple different ways, especially if while deploying it, we got to think of all different scenarios. Some scenarios are, we got to be more risk averse, we got to be more rigorous, right? So the best way to evaluate this framework would be to implement the recommendation from this framework and test that against one winning arm, right? So let's say we didn't do the fractional factorial designs. So that one is too costly to implement. It just, the calculation that I talked about earlier, it just says that it's going to take, implementing that is going to take a few months. And so that one is not done. Instead, what we can do is something similar to what you're saying, which is within the sample of 8, how good are we predicting? So that is something we did, and we do a good job over there.
Also, a quick question also. Did you optimize in any way the design of the fractional factorial design? I think you have 9 arms. I think you have 5 coefficients. I think that you estimate probably. Did you try to have an orthogonal design, or did you? Yeah.
So we used the no interaction orthogonal design for the purpose of this particular application.
And this one has 9 or 8?
8 experimental arms.
So, but you have 9. You use
the 9th one is the out of sample, which we use for
thank you.
Which we use for evaluation.
Thank you.
And that gives us a lot of data points to check whether the assumptions actually hold.
Thank you.
So I had a question about the objective you started with, optimize retention, right? So I was right away thinking, but what about costs? And so, of course, in your specific application, you completely stay away from that one because you don't have the size of the discount, you have only how it's framed, right? So all of these things cost about the same. Now, there was another practice price paper, I think about 15 years ago, where, dynamic pricing, where the result was, hey, do this, and then management said, oh, no, we also have other objectives. So is this technique also applicable if there's an actual trade-off, if you're talking about the size of the discount, for instance?
Excellent question. Yeah, so I think I have seen that paper. So the Y variable we use over here is net of the costs. So that is important. So the Y variable is the incremental revenue that's coming and net of the promotional cost that you're spending on it. So there could be another cost that you can add, right? So in this case, the arms were similar in the discounts that they actually give. I think the design can incorporate that because in the evaluation stage, when we have the maximum policy, we can subtract the cost that you're spending per customer at that stage and accommodate that. But yeah, that's a good question.
My other question was about personalization, right? So I talk a lot with algorithms. So your indeed is based on behavioral variables, past spending, right? And you don't have demographics, but it could be that your rule kind of gives more to certain people of a certain demographic, right? So maybe past spenders are, a certain kind of type of folks. And if you have to explain your algorithm to the government, for instance, there may be some bias in there. So given the fact that it only gains you 2% to personalize, wouldn't that be a good argument for the company to say maybe we shouldn't personalize because we get all of your wonderful gains without going into that, segmentation or, third-degree price discrimination, as people may call it?
Yeah, 2% of the revenue in this case is pretty significant. When you multiply that with a few 100 million, it becomes pretty significant. But you're right. The nuances that come with using different data for prediction are, they remain the same whether you use A/B testing or you use fractional factorial design. But these are very important considerations for applying this.
Just a really quick one for me and Navdeep. I have to say I didn't think factorization could be done with such passion and dynamism, but you really have brought it to the table. You sell it to us in terms of reduced time, reduced costs, increased revenue. It sounds like a winning combination right there. But in reality, in selling this concept to DoorDash, what did you say was the trade-off? What would you say was the trade-off?
So practically speaking, we see, so I encountered a lot of very, very smart statisticians who are very well in tuned with what's being developed in the machine learning world and the causal inference world. So people have taken very different perspectives in speaking over there, and the whole narrative is dominated by what I was alluding earlier, which is how can we make the testing most efficient? And by testing, I mean statistical testing. So the whole team is very much into coming up with the best controls, using machine learning, using the best causal inference to reduce noise. This approach, which comes out of marketing and more business side of the statistics and less the engineering side of it, was for some reason not being implemented. And I think that's a great question. The question I ask also myself, which is, why is this on the table? This should be done, not now, way earlier. And I was looking for applications which actually demonstrate the gains from this, and I couldn't find any. And I think, and this is my personal take, that I think the factorization is more thought about on the business side. And a lot of the colleagues that I met while implementing this are from the engineering side, and they're very much into just make the right-hand side variables less and less noisy. Just take out the noise from the process and make it efficient. And this just complements all of that. Yeah.
I have a question. This is, in my point of view, this is a very clever idea. So I'm just curious. It's based on the fundamental assumption those different treatment arms are independent, right? So in practice, there could be scenarios that maybe some of the treatment are correlated. So have you and others at DoorDash thought about how you would relax your method to kind of take into account the fact that if like two treatments are correlated?
Yeah, that's a great question. That's a very fundamental question for us over here. So as we go out from this particular application to other teams, there might be situations where these interactions are known to the team and they know that this has to happen. In that case, the experiment design can accommodate that. The only thing that's going to happen is that now the number of arms that you need in an experiment are going to be larger. So once you say that is the truth in my team, all that is telling our system is that, okay, so you got to be ready for a more complicated experiment, and that can be accommodated over here. I think for us, the insight was that a lot of the teams, when you talk in these terms, the assumption becomes very salient. But when you look at the status quo, the assumption is implicit, because when you do sequential testing, you are actually not thinking of these interactions. So it's there. So I think we bring it out and we give a way to actually test it and test it using data and look at how impactful it could be.
Thank you so much.
Thank you.